Okay, we are ready to start our last unit. These three chapters, 26, 27, and 28, are on what's called hypothesis testing. And we're going to talk about a few different types of hypothesis tests. Just as we go through this, you'll see what a hypothesis test is. So, we've got this coin right here, and it's damaged. So what we want to know is this coin still fair? And so the assertion is, yes, the coin is still fair. It's the same amount taken out of the back as front. So it's still just as likely to get heads or tails. So we're going to make a box model. We either get tails, that's a 0, or heads, that's a 1. And that's because we're looking at the percentage of heads. So heads has to be 1. And we're going to toss this coin 100 times. We want to know what the expected percentage of heads would be, give or take how much. So with this, you can see the word expected and give or take how much. So that tells you we're going to be working with EV and SE still. That's EV sum and SE sum because we're looking at the sum of the heads, how many total heads we got. So the expected number of heads is 50. We know that without having to do any work. The SE, if you remember our formula from exam 2, SE is equal to the standard deviation of the box times the number of draws. And the standard deviation for 0 and 1, we've done that 1,000 times throughout the notes and the homework. The standard deviation for 0 and 1 is 0.5. If you don't know that just off the top of your head, you can go into stat, edit, 0 and 1. And then we can go stat, calc, one of our stats. And nothing's there. Stat, edit, 0. Oh, I didn't get the 1 typed in. That's why. Okay, so we can see the standard deviation is 0.5. And it's 0.5 times the square root of the number of draws. Sorry, I forgot that square root on it. So that is 5. So we expect 50 heads, give or take 5 heads. So we expect 45 to 55 heads. Okay, let's look at what actually happens. We toss the coin 100 times and we get 53 heads. So remember, we expect 50, give or take 5. Or 45 to 55. Okay, that's for one standard error away. 2 standard errors would be 40 to 50 because it's 50, give or take 2 times 5. So 53 is within 2 standard errors. So that's pretty reasonable. We can figure out exactly how many standard errors it is away from the expected value. This is just asking for z-score when it asks how many standard errors away it is. So we can do z is equal to 53 minus the expected value. Ooh, sorry, this should be 60, not 50. That's probably been bugging you. Okay, 53 minus 50 over the expected value of 5. Oh my goodness, you guys. 53 is within 1 standard error away. Just messed that up. Okay, so 53 is within this range. Wow. To be exact, it's 3 out of 5 or 0.6 standard errors away from the z or from the expected value. So what I want to know now is what is the chance of observing this result or something more extreme. Okay, that is asking what the chance of observing 53 or more is. So that's saying if you have your normal curve, we expect 50. What's the chance of getting 53 or more? So what we've actually done here is step 1. Step 2, average and standard deviation. We use that to get step 3. Step 4. Step 5. And step 6. Shade norm. 0.6 or more extreme. So 0.6 to 10 to 0 to 1. And then we type that into our calculator. And we get 27.4%. So the chance of observing a 53 or more is 27%. So that's fairly likely. I mean, it's kind of low, but it's not way out there. So it's possible. Okay, here's a look at what we just did. Now let's look at the second option. I toss the coin and get 63 heads. Remember, we expected 50, give or take 5. So 63 is, let's see, 63 minus 50 over 5 is 13 over 5. That's almost 3 standard errors away. 2.6 standard errors away from the expected. So we want to know the chance of observing 63 or more. So shade norm, 2.6 standard errors or greater. If you listen really close, you might be able to hear my dog snoring next to me. Oh, now she stopped. Darn it. I'm sure she'll do it again. Okay, that is a 0.5% chance of happening. So that's pretty unlikely. So this 53 had a 27% chance of happening versus the 63 had a 0.5% chance of happening. So we have a couple different options here. If we get a 53% heads, then the coin is probably still fair. Versus if we get a 63% heads, the coin is probably not fair. And this leads us right into hypothesis testing. In fact, we just did a hypothesis test. Our assertion is that the coin is fair. That's our hypothesis. And then we just went through a couple different results and saw, oh, yeah, that's likely to happen, so we can believe our hypothesis, the coin is fair, if we got 53 heads, versus 63 heads, that's not very likely to happen, so the coin is not fair. We can see that small, tiny 0.5% chance. Okay, this is just what we explained. If an observed value is too many SEs away, so for example, we got 2.6 or 0.5% chance of it happening, it is hard to explain by chance. We can't say we got 13 too many heads just by chance. It's because the coin is not fair, or it looks like the coin is not fair. In statistics, we won't ever say, yes, for sure it's not fair. We'll just say, it looks like it's not fair. the steps that we just went through, we're going to formalize them into our steps for a hypothesis test. Step 1 is to state the null and alternative hypothesis or alternate hypothesis. So remember, a hypothesis is just something you think is true, and then in science you go through a bunch of steps to prove it, and then it becomes a theory. Same type of thing in statistics. We have this hypothesis that we think is true, and then we're going to go through some formulas to show either yes, this hypothesis works, or no, it does not work. So the null is always that there's nothing wrong, that it is what we expect it to be, versus the alternative is that there is something wrong. So for our coin that has a chunk taken out of it, the null is the coin is fair, or we're going to get 50% heads. Versus the alternative is the coin is not fair. We're going to get more or less than 50% heads. So the alternative or alternate, you can use both words back and forth, hypothesis is what you were trying to show evidence for, and it's often the opposite. Actually, it's always the opposite of the null hypothesis. So our null was we're going to get 50% heads. The alternative is we're not going to get 50% heads. We're going to get more or less than 50% heads. Okay. Step 1 was to write down the hypotheses. Step 2 is to calculate Z, and it's just our normal formula, what the number we want minus the expected value over the standard error. Depends on if you're using percentages or averages for which formula you use to get the expected and the standard error. Then you calculate what's called the p-value. And we know how to get the p-value. We've done it over and over and over again. We've just never called it the p-value. The p-value is simply the number you get from shade norm. That's now our p-value. So it's the percent or that chance of that happening. So the p-value is the chance of observing the sample statistic or something more extreme farther away from the EV if the null is true. So if this coin is fair, what's the chance of getting 63 or more heads? And then if Z is positive, so if we get a Z that's above, we do that number to 10. If Z is negative, or we're looking at a number below the average, we do negative 10 to that number. Okay, the last step is to make a decision. The last step is to make a decision. And with that, we're going to take that number from our p-value or from shade norm and decide if the coin is fair or not fair, or whatever we're testing, if the null or the alternative is likely to be true. If the p-value is less than 5%, we reject the null hypothesis. For example, when we got 63 heads, we got a 0.5% chance of that happening. 0.5% is less than 5%, so we're going to say it appears that the coin is not fair. We're rejecting that null that it is fair. It is not fair. If it's more than 5%, we say, yeah, it looks like this coin is fair. There's a 27% chance of it happening, so no problems here. It's probably fair. Juno, out of the front room. Sorry, I have to yell at my dog every time she goes in the front room. Okay, so we're going to look at an example here for null hypothesis. A magazine claims that 50% of young mothers say finding childcare is a problem. A local childcare referral group takes a simple random sample of 450 young mothers, so notice it's random and it's large, and find that 210 of them say finding childcare is a problem. This might sound familiar to you. Because we have worked with this problem before. We're just going to extend it into a hypothesis test now. So what we want to know is this evidence that there is less of a problem in this specific area than there is nationwide. So our hypothesis, the null, is always that it is what it says it should be. So 50% of young mothers have a hard time finding childcare. Oops. Okay, that's our null. Just, it is what it should be. It should be 50%. Okay, then we've got the sample, 210 out of 450. If we calculate that percent really quick, 210 divided by 450, that is 46.7%. So what we want to know is if that is a big enough difference from 50% that locally there's less of a problem finding childcare. So our alternative is less than, because 46% is less than 50%. 50% of young mothers, young movers, have a hard time finding childcare. Okay, so we've got the null. That, yeah, it's 50%. That's what it should be, so that's what it is. We've got our alternative that it is not what it should be. The test statistic is Z. So we had 46.7% when we should have expected 50%. What we don't have here is our standard error. That's what needs to go on the bottom. But we can calculate our standard error. So the standard error is going to be the square root of the percent of ones times the percent of zeros. But we have two different numbers here. Should we be using the 0.5%? Or should we be using, the 50%? Or should we be using the 46.7% for our percent of ones to calculate the SE percent? And it's always going to be, let me double check this, but it should always just be what you expect it to be. So it should be the 50%. Just going to grab my notes, double check so I don't tell you wrong. Whoa. Okay, yep. It should be. There we go. 0.5, or the square root of 0.5 times 0.5, because 50% of mothers have a hard time finding childcare. Whoops. %, do not. That's our standard deviation. So then we need to divide it by the square root of the number of draws. And our number of draws was 450. And that gives us a standard error of, oh, and then you have to multiply it by 100%. 2.36. Okay, so our standard error is 2.36. If we do this arithmetic, we get negative 1.41%. So then our p-value is what we get when we do shade norm. Okay, and what we're looking at is a negative p-value. If it's below, you always do more extreme. So below means less than that. Above means above the average would mean less, greater than that. So shade norm, we're looking negative 10 to negative 1.4101. And we can type that into our calculator. Get 7.93%. So then our p-value is 7.93%. 7.93% is greater than 5%. So this is our level of significance, that 5%. And since we got a number that's greater than it, we fail to reject the null. A number that is more than 5% means you fail to reject it. So what that means is 46% is not significantly different enough from 50% that we think there's a difference between that local town versus the nation. So we will say we fail to reject the null. Or in other words, we accept the null. Statisticians just don't like accepting things because they don't like being held accountable for anything. So we fail to reject the null. It looks like it this city, town, whatever it is not significantly different from the nation. And that's assuming the 50% is for the whole nation. Okay, there's your first example. Hopefully you just kind of understood what's going on here. Let's do another one. And I'll go through it step by step again. But before we do that, let me show one more time what steps I took here. So step 1 is to write your null and your alternative. Your null is basically given to you in the problem. 50% of young mothers have a hard time finding childcare. Your alternative is there is less of a problem locally. Okay, then we went through and technically we should have done step 1, draw the normal curve. Step 2, find the average and standard deviation. Step 3, find your expected value percent and your SE percent. Step 4, draw the normal curve. Step 5, shade norm. Step 5, z-score. Step 6, shade norm. I just kind of breezed through those because we've done those steps so many times in the last few chapters that I don't feel like we need to do every step, but I'll probably just do every step from now on just to make sure we get them all. And then so that was step 2. And inside step 2, we had 6 steps. Step 3 is to take the shade norm number and interpret it. 7.93 is bigger than 5%, so we fail to reject. And then step 4 is to just write our conclusion. We failed to reject the null. So it looks like this town has just as much problem finding childcare as every other town. We reject the null hypothesis when the p-value is small. What that's saying is if the p-value is small, it means it's a small percent, which means small chance of event happening. And by event, I mean the null. So, must be a problem there. Meaning we reject the null. We say there's something wrong with this null, so we don't believe it. At one large university, 71% of all students graduate within 6 years. A random sample of 150 athletes from this university was selected, and it found 97 of them graduated within 6 years. Is there evidence that less than 71% of athletes graduate within 6 years? Okay, you've probably seen this problem before because we have done it in previous notes. First step is to write the null and the alternative. The null is that it is what it should be. 71% of students graduate within 6 years. And in this case, we're talking about student athletes. So I'm going to say 71% of student athletes graduate within 6 years. Okay, then this last sentence says, is there evidence that less than 71%? So the alternative is less than. 71% of student athletes graduate within 6 years. Okay, test statistics. So we're going to do the 6 steps here. Step 1, make a box model. 71% graduate. That leaves 29%. 100 minus 71 is 29. Do not graduate within the 6 years. And we are looking at a sample of 150. Okay, step 2, average and standard deviation of the box. We're looking at the average and standard deviation for percents. So let's go to our cheat sheet from exam 2. Okay, with percent, we don't need the average. The standard deviation is the percent of ones times the percent of zeros. .45. Step 3 is the expected value percent. We expect 71% because that's the number we were told. Standard error percent. Is standard deviation of the box divided by the square root of the number of draws. 0.45. Sorry, my phone is blowing up and I don't know what's happening there. I'll look at it later. Divided by the sample size, square root of the sample size times 100%. 3.7%. Okay, step 4. This is where we need to see what actually happened. 97 of 150. (64.7%). So we expected 71%, but it actually was 64.7%. Okay, with hypothesis testing, you always do more extreme. So if it's less than 70 or if you're less than the expected, you shade below. So step 5, z-score. (64.7% minus 71% over 3.7%. Because they're all percent, you don't have to change them to decimal. Oh no, my Apple Pencil's almost dead. Okay, then step 6, shade norm. -10, -1.701. So that is 4.5%. Okay, our p-value is 4.5%. That is less than 5%. So let's go back and look. If P is less than 5%, we reject the null. And what that means is it looks like, if we look back at our null and alternative, since we're rejecting the null, that means we're kind of accepting the alternative, except we never say we accept something. But what we're going to say is it appears that less than 71% of student athletes graduate within 6 years. So we're saying just what the alternative says. So what this means is the 64% is significantly, the 64.7% is significantly different enough from 71% that we think that student athlete population is slightly different than the general population because of how significantly different that is. Okay, let's look at this example again. So with light bulbs, the last two we looked at were percents. We're now going to look at an average. A manufacturer claims that its light bulbs will last for an average of 500 hours with a standard deviation of 20 hours. So average of 500, standard deviation of 20. So that's our box. Average and standard deviation. Consumer organization selects 40 light bulbs and finds that their average is actually 487. Is this evidence that the manufacturers are lying, that the average light bulb is actually below 500 hours. So step 1 are null and alternative. Null is just what we expect it to be. Light bulbs will last for an average of 500 hours. And that's from this specific manufacturer. Okay, the alternative is the average lifetime is below 500 hours. So, light bulbs from this manufacturer will last less than 500 hours on average. So now we just want to see if 487 is significantly different enough, meaning too many standard deviations away from what we expect, that we think this manufacturer is exaggerating their light bulb life. Okay, step 1 is our box model with averages. The box model is not needed. Step 2, we already were given the average was 500 with a standard deviation of 20. Step 3, the expected average is what it should be, that 500 hours. With the standard error average, we can look back at our formula. Standard error average is the standard deviation of the box divided by the square root of the number of draws. How many did we draw out? 40? Okay, 3.2%. Or sorry, 3.2. It's not a percent because these are averages. Step 4. We should see 500. What we actually saw was 487. Did I get that number right? 487. And we always want more extreme. So if it's less than what you expect, you shade to the left. If it's more than what you expect, you shade to the right. Step 5, z-score. So 13 divided by 3.2, that's going to be fairly large. 4 standard deviations away, 4.1. Or standard errors away. So if we do shade norm, sorry, that should be negative. Negative 10, negative 4.1, 0, 1. When you type that in, you're going to get approximately 0% because 4 standard errors is so far away from the expected. So 0% is less than 5%. And if you look way back, when you have less than 5%, that means we reject the null. So essentially you're accepting the alternative. So we can look back. Our alternative is less than 500 hours on average is how long the light bulbs last. So we're going to say there is evidence that the light bulbs last less than 500 hours on average. Is this our last example? 2 more examples. Okay. Let's do this one. Okay. Data from the CDC indicate that for females aged 35 to 55, the average BMI is 25.12 average. Assume the standard deviation is 6. Recent study of 100 female cardiovascular technologists who were registered in the U.S. and were within the same age range, and they found that their BMI was 24.47. So the sample was 24.47. Is there evidence that cardio techs have a lower BMI than general females in the nation? So hypothesis. The cardio techs average BMI is what it should be, 25.12. So this is for all cardio techs. We did a sample and got 24.47. So we want to know if that's a big enough difference that we're wondering if that average is actually not right. So the alternative, 24 was less than what we expected. So cardio techs average BMI is less than 25.12. Notice I didn't use the sample average in there at all, because that sample average is simply for a few of these cardio techs. It's not for all cardio techs. So I'm not talking 24.47. We're going to use that 24.47 to get our p-value in a few minutes, but that's the only time it's used. So step 1, we're talking averages, so we don't need a box model. Step 2, we were given the average, 25.12. Let me double check that number. Yes. Standard deviation, we were told, is 6. Step 3, we'd expect an average of 25.12, because that's the number we were told, with a standard error of standard deviation divided by the square root of the number of draws. So 0.6. Well, we got, when we sampled 100 females, cardio techs, we got 24.47. So it should have been 25.12, but we actually got 24.47. So we want to know less than that number. Well, that z-score is just negative 1.0833, so I'm going to say negative 1.1. So shade norm, negative 10 to negative 1.101. This should be a pretty big number, because negative 1.1, that's a very reasonable standard error. That is 13.6%. Okay, 13.6 is bigger than 5. So there's no evidence that these females in the sample are really any different than general females throughout the whole U.S. So we fail to reject the null. Or, in other words, we're accepting the null. We just don't typically say the word accept. And we say, it appears the average for female cardiotechs is no different than average for all females. Whew, okay. Okay, this last example, do less than 25% of U.S. adults smoke. In a random sample of 1,018 adults, 224 said they smoked a cigarette in the last week. So let's figure out that percent real quick. That is... Oh, I missed a 2 when I typed that in. 22%. Okay, so it looks like less than. We just need to decide if that 3% is big enough that we can conclude it actually is less than. So no, 25% of U.S. adults smoke. The alternative is less than. So the null is always, it's equal to the percent it should be. The alternative is always it's less than or it's greater than. Less than 25% of U.S. adults smoke. Okay, step 1 is our box model. 25% do smoke, 75% do not smoke. Step 2, average percent. So with percents, we really don't need an average. Yeah, average of the box is not needed. Standard deviation of the box is 0.25 times 0.75. Or 0.1875. So I'm going to round that to 0.19. Step 3, the expected value percent. Well, we'd expect 25% because that's the number it gave us. SE percent is 0.19 divided by the square root of the number of people sampled times 100%. Okay, step 4, we got 22%, but we expect 25%. That's less than, so we shade below. Step 5, Z is equal to 22 minus 25. So what we want minus what we expect over the standard error. That is -5. So step 6, shade norm, -10 to to -5 to 0 to 1, that is 0%. 0% is less than 5%. Because -5, that's a very, very large standard error. Remember, we typically just go to 0 standard deviations or 3 standard deviations or standard errors. So since it's 0%, that's less than 5%. So we can conclude that we reject the null. If we look back at what we said for the null, we don't want this one, so we want this one. It looks like it's less than 25% of U.S. adults that smoke. And we're going to say it appears that less than 25% of U.S. adults smoke. Okay, there's your first work with with hypothesis testing. Here's the homework for chapter 26. The next chapter or the next notes do cover a little more on chapter 26. So if you're working on it and you're like, we haven't learned this yet, watch the next video. I'm going to give it to you right now so you can get started. But I should have the next video up hopefully by the time you're ready to work on the homework. So I'd recommend watching the first half of the next video before you actually work on this homework. It's due Friday, May 15th. You want to get it done as quickly as possible because our final is the 22nd. So you need to get it done, the homework done quickly so you can start preparing for the final, because our final is not going to be open note, open book. It's all going to have to be memorized except for the formula sheet you'll be given. And yeah, this is the